The signal-to-noise ratio is a very common figure of merit to evaluate the performance in communication systems. The name is self-explaining. The signal-to-noise ratio is a ratio between the power of a signal and the power of noise. And here we are going to compute the signal-to-noise ratio at the input of a receiver, before of filtering and after filtering the received signal and the thermal noise. The problem statement is that at the input of the receiver, we'll have a signal x of t with a given power px and this random process here, and we'll have also the thermal noise n of t with the corresponding statistical model. An stationary energodic wide and Gaussian process with power spectral density equal to n0 halves. Then at the receiver we have a filter, and y of t is the output of the filter for the signal, for x, and z of t is the output of the filter for the noise, the filtered noise. And we'll compute the signal-to-noise ratio here and here. At the input of the filter, basically we have the ratio between the power of x and the power of the thermal noise. And at the output of the filter, we will have the ratio between the power of the filtered signal y and the power of the filtered noise z. If we start at the input of the filter, basically we have the ratio between the power of x and the power of the thermal noise, but theoretically the power of the thermal noise is infinite. So theoretically the signal-to-noise ratio at the input of the receiver is 0. In decibels we have 10 times the logarithm with a base equal to 10 of this ratio. We have minus infinite decibels. Therefore, it is mandatory to filter at the receiver input to limit the power of the thermal noise. Now, at the output of the filter, we have the ratio between the power of the filtered signal and the power of the filtered noise, and the corresponding value in decibels. To compute these values, typically the power of the filtered signal can be obtained by integrating the power spectral density of the output signal, the filtered signal y of t. And remember that the power spectral density at the output of a linear system is equal to the power spectral density at the input times square modulus of the frequency response of the filter. Depending on this frequency response, we'll have a given signal power in this numerator here. For the noise power at the denominator of the signal-to-noise ratio, we have several alternatives. In general, this noise power can be always computed by the product between n0 halves and the energy of the filter. But if we consider ideal filters, we have very simple expressions. With unit gain is just equal to the product between n0. Remember that n0 is the product between the Boltzmann constant and the temperature in Kelvin degrees, the product between n0 and the bandwidth in hertz. If we have a gain power in the ideal filter, the product with this power must be included. The product with this gain power must be included. If we have a non-ideal filter, but we know the noise equivalent bandwidth, we can use the equivalent expression, n0 times the noise equivalent bandwidth times the power gain of the filter. This is how the signal-to-noise ratio at the output of the filter can be computed. In general, now we'll have a non-zero signal-to-noise ratio, and the higher the signal-to-noise ratio, the better the performance of the system. This is a figure of merit that can be used to compare different systems.